Apologize for my lateness. The oil light came on. I'm on a motorcycle, so I don't want to push it. Unfortunately, I wasn't too far from home. I looked back, put in some oil. It was bone dry. About halfway here, the battery light came on, and I wasn't sure I was going to make it. But I don't know if I'll be able to get home, but we'll see. It's been running perfectly up until now. It's like everything goes wrong at the same time, right? First, on exams, we took an exam on Tuesday, right? So I've got those. I've got the Monday class. I'm giving another exam after this class, so this weekend I will be scoring exams, and then I will post them. But I will wait to post the exams until I have them all in there. So I'll do it as expeditiously as I can, but it might not be till Sunday night. Could be as early as Friday night if I get some, maybe I could use AI to help me or something. No, I don't know. If I can get it done fast enough. Last time it took almost 20 hours to score and scan them in, but I think it's a good idea for the scanning. So here, as we transition to the next set of content, is that at this point we've actually covered, we've gone over most of the skills we need, almost all of them. And what we start doing now is we do what's called an integral, so we're going backwards, literally backwards. So far we gave you a function, we wanted you to get its derivative. And what was the derivative? What does the derivative give us? The rate of change, instantaneous rate of change, right? So it tells us how we're changing, not where we're at. The original function gave us values, like how much profit we're making, how much cost things were. The derivative gave us the rate of change, so we could use that as a marginal and see what's the next thing going to cost. What we do now is we take that derivative, we start with the derivative, and we're going to go back to the other function. Okay, so we're starting with a rate. We're given a rate of change, and we want to know, well, if this is the rate of change, what would be my total profit? What would be my total cost? So those are the types of questions we'll be able to answer just by knowing how fast things are changing. Okay, so this comes in handy if if you've got a leak and you can measure how fast your boat's leaking, how fast is the water coming in. You'll be able to calculate how soon, or when will your boat be full of water and sinking, that kind of thing. So sometimes we need that. We don't, we've got the rate, but we need to know, okay, how much trouble am I really in? Those kind of things. So that's what all this is going to give us mathematically. What we're doing is we're starting with the answer. It's like Jeopardy, right? We're going back to what's the question. That's all we're doing. So you're going to see today we'll take a lot of the things we've already learned. We'll do them sort of what I would call the forward direction. And then we're just going to think of the steps, and we're going to do everything backwards. When you do things backwards, what happens? So like you're taking an engine apart, right? You go lefty-loosey, right? So you go to, when you want to take it apart, you go to the left. When you put it back together, you're going to go to the right. Yeah? And when you take something apart, you start on the outside and work in. When you put things back together, you got to start on the inside and work out. So two things happen is not only are you doing things in the opposite direction, you're also doing them in the opposite order. Okay, so we'll see all of that's going to be what we're doing today. And sort of in one page, we're going to go through and we're going to get the whole lesson done, and then we'll look at some examples. And of course, in math, they have special notation, so we'll look at the special notation, the special vocabulary, but we'll be able to see how it all works. So first of all, I want to just kind of highlight where we're at with our schedule. So remember, it's changed a little. The elasticity 12.6 is an extra credit activity, so you're still welcome to work on that. You can wait till the end. You can wait till we get to finals week. Whatever you want to do, but it'll count as one extra assignment, so that's helpful. So we're getting into what's called the indefinite integral, and we have 1, 2, 3, 4, 5 sections that we'll be going through before the next exam. And then after that exam, there's only 3 sections that we'll be doing that will be on the final. So the final is comprehensive, but there'll only be these 3 sections that we haven't tested you on that will also be on the final. So we'll talk about that later. But we've got one more exam coming up. So now's a good time to start. Once I get test 2 up, especially look back at your test 1, your test 2. Anything you didn't get right, try to figure out, how you could do that. Also, I had a student come up in my Monday class and asked about scoring, and I says, I'm happy to look at things. I'll be honest, when I'm scoring everything, I've got about 1 to 2 minutes per paper, and I've got to look real quick. And so I look for the answers and I look for the explanations. If the answer was wrong, oftentimes I might be a little brutal on you, like I was on him. We went back and said, yeah, your answer's, oh, I see. It was, I didn't see it when I was grading, but I was able to say, yeah, you should have got more points for that. There's the one on the marginal in your explanation. You needed to make reference something to the next one, and he said, like, it's the average, so I marked it wrong. But then later on, he says something about the 201st. I said, okay, I can give you half for that. So what I want you to do is I want you to look through your particular one, and it's in Canvas. I scanned them all in. See if, and I'll be honest, we can have an honest conversation when I get here next time, before class or after class, or we can set up a Zoom meeting because we'll both have access to it. And I'd be happy to go step by step. Could I get a couple extra points here because, I was on the right track here? And I'll just be honest, I may have missed it, and then again, in that case, I definitely did. Because I look, oh, this time now, I looked at, you were just off by you had a negative when you should have had a positive, and that threw everything off, so it was like 3 steps. So I says, I should take a point off here for that, but I shouldn't take the points off here. So anyway, I'm happy to do that, and it's a good activity because it'll get you reviewing the exams, get you advocating for yourself, and then we can have that conversation, and it will help you do better on the final. Okay? Because you've made it this far, let's make sure that you can pass that final. So I always say is, that final exam, like I've been saying, is it's comprehensive enough. If you can pass that final, you will pass the class regardless of the other things. So if you haven't done well. Now, if you've done well on the exams, the good news is you don't have to worry too much about the final because you've got a strong score showing you've understood those things, so that helps. But if you haven't done as well as you'd like, or, maybe you think, that Canvas might say you're failing, do the homework, and you should be able to make up everything. If you can't, send me an email. I'll make sure that they're extended so by the end of class you're able to work through all the homeworks, because that will help you learn it. Do well on the final, at least earn a passing grade, and then we can get you through this. We get you this pass, so that you can go on to the next one. And math is not your major, probably. If it is, you're in the wrong class, but probably business is your major. But you will use this math, and we want to make sure you have at least, a 70% understanding of the by the end. Okay, so we'll work at that. It's not on the syllabus. It's not anything, but I'll just tell you that if you can pass the final exam with a 70% or better, regardless of what's happened, you will at least earn that C, right? If you've been doing well, we'll get you there too. So anyway, keep moving forward. So let's go ahead. And the reason I also mentioned all of that was because even he was kind of, I'm not sure if, he was kind of shy about approaching me and thinking, I don't mean to be asking for points, but I'd like to ask for some points. That's okay. It's okay. I'm not perfect, certainly. I miss things. And I says, especially, I know when I'm grading, I got to get through 200 exams, and I get a minute. And so especially if you're, I apologize because there's some, depends on where you are in the alphabet. If I've been grading for a long time, Yeah, I'm fuzzy-headed, but what I do is I count on you to take a look and keep me honest, okay? And we'll make it all work. See, I am recording, aren't I? I hope. Maybe I'm not. Yeah, I must be recording. Okay. Well, if not, we'll use the other one, but it looks like I'm recording. So, here we go. So the indefinite integral, we'll explain what that really means and everything. But what the indefinite integral is, an integral is mathematically they used summations to get back to that. So if you know the rate of change, basically we're going to see one of the things an integral is, it's the area under the curve. Remember, the derivative was a tangent line to the original function, so it was the slope of the tangent line. What we're going to do is now, if we have all those slopes, so if we have, remember, we're starting with the derivative function, if we take the area under that curve, that and add those all together, that gives us the value of the original function. So we call that the integral. So we're going to think of, in terms of what we're doing, is basically the area under the derivative curve is what we're getting physically. We also call it the antiderivative. I like to call it the underderivative, but that's just my terminology. We're starting with the derivative. We're going back to the function we started with. Okay, that's all. That's what an integral is. So what do we know about derivatives? Let's start with what we know, and then we'll see that we sort of already know how to get an antiderivative because we've got the process. And this is where I mean, I always forget to do this, that we well, we already know. Remember, I don't know if you remember, but early on, maybe the first day I says, do you know how to subtract one? You say, yeah. Do you know how to add one? Yeah. You can do calculus. That's basically what we're doing. So now's the time to add the one instead of subtract the one. So let's start with the function. I'll try to stick with sort of the notation. We'll call this big F of x. And let's just put up here 3x to the fourth plus 5x to the third minus 2x plus 4. Okay, and what we want to do is we want to get the derivative of this function. Okay, so just walk with me as we do this together, and this should be something that shouldn't be a challenge for us too much, right? What do we do? But what we want to do is we want to explore each of the steps. So 3x to the fourth, we take its, and we're going to take the derivative step or term by term, right? What's the first step we do when we take the derivative of this first term? So we take this exponent and multiply by the front. What's the second step we do? Subtract 1 from the exponent. Good. So those are the two steps that will give us that the derivative is 12x to the third. Okay, so we've been doing that. So just think of it. Those are the steps. Think of it like a dance or whatever. What we're going to do is we're going to do it in the reverse order, and we're going to do the inverse stuff, right? So instead of subtracting one, we're going to add one. Instead of multiplying, what are we going to do? You got it. So those are opposites of each other. So we'll get there. Then we'll do the next step, right? 3 times 5, we'll go a little bit faster, is 15x squared, subtracting the 1. Over here we've got a 1. 1 times 2 gives us a negative 2. X to the 0, so that's, we don't write that, but you could. And then derivative of 4 is 0, right? Okay, so I wanted you to see each of those steps. Now in this class, this section, what we're trying to do is we're going to do something called the integral. So we start with the derivative. Let me see my notation. And so oftentimes what they'll do is they'll relabel this as a function. They'll call it little f of x. Okay? So what they're telling us, this is the symbol for the integral. So you're going to see that a lot. So just like the little prime was the symbol for take the derivative, now we got this little sort of S curve. And that's actually what it's from summation. We'll see that a little bit later. But we want to take the integral of little f of x. And remember what f of x is. It's a derivative. So I almost forgot. What we put in this symbol is we put f of x dx. And that indicates that what we have in there is a derivative, right? It's not dx dy or dy dx or whatever, but just the dx, so it's the derivative of x that we've got in there. So what we're really doing is we're taking the integral of 12x to the third plus 15x squared minus 2 dx, and let's see if we can do it. So we want to find out, this is a derivative, what was the function beforehand? Again, we kind of got it up there, but let's think if we didn't see that, if we covered it up, how would we go about getting the derivative? Well, we would go backwards, right? So this was the first step, this was the second step. So we will start with the second step, right? We will. Well, no, we won't. What will we do first? We want to add 1 to that exponent first. So we got to do this backwards, otherwise, yeah. So we're going to add 1 first. Then we're going to take this new exponent, because that's what we did first. So we actually got it, it's now to the 4th power, isn't it? What are we going to do with that 4th power? We're going to bring it down in front, but we're not going to multiply. We're going to divide. Okay. So, and I'm going to write it this way just to remind you, it's the new exponent. So I'll put it as 3 plus 1, which is 4. So to get this integral, we're going to get 12. Actually, I'll do this. I'll do it double steps. 12 divided by 4, x to the 4th power. We just integrated. And doesn't that kind of look like what we started? We had 3x to the 4th. 12 divided by 4 is 3. I'll go ahead and go to the next step. Yes, we got that first term. We got back to it by doing things backwards, right? Reverse order and opposite. Let's go to the next step. What do we do? 15x squared. First thing, add 1. Always just adding 1. Because to take the derivative, we subtracted 1, so we got to go back. And then we divide by what? The new exponent. So we're going to get a plus 15 divided by 3, x to the 3rd power. 15 divided by 3 is 5, x to the 3rd. Ooh, that's what we had up there. It's looking good, right? Looking good so far. Now what about this minus 2? This gets a little tricky. What do we do with it? Kind of see up there, but up here I subtracted 1, right? And then, or I multiplied by 1. What probably the best way to think of this is really 2x to the 0 power. We don't write that because x to the 0 power is primarily 1, as long as x is not 0, right? So just call it x to the 0 is 1. Now let's go ahead and do all this same steps. So because this gives us a way to move forward. We're going to add 1 to the exponent. So 0 plus 1 is, we're going to get x to the 1st power, right? And then we're going to divide by 1, but that doesn't change anything, right? 2 divided by 1 is still 2. But I'll write it just so, you know, 2 divided by 0 plus 1, the new exponent, x to the 1st power. So we're going to get minus 2x. Oh man, that's beautiful. We've got almost everything we've got. But how would we know to put 4? Right? Because we got a plus 4 up there. We can't. There's nothing that tells us that that constant would be 4. So when we're integrating, unless we have an additional piece of information, and there's one in the examples that'll work that does that, unless we have additional information, we know there could be a constant, but there's no way to know what it is, so we put plus C. Or I think the book uses plus K for, but constant starts with a C, doesn't it? They use K, I don't know why, but anyway, we'll just do plus something. We know there could be a number there. So what we found out is we can get pretty close to going back, but because taking a derivative, every constant becomes zero and sort of just disappears, we have destroyed part of our function. We can't get back to that unless we know something additional. Okay, does that make sense? So this that's why they call it the indefinite integral, because this is not exactly the right formula. It's close, but there's an infinite number. C could be like 1,000,000. It could be -5. It could, we don't know. It could be anything, but it's close. So it's called the indefinite integral. We're going to see. We're going to quickly become. We'll get the definite integral when we have enough information. We don't need that C anymore. Okay, or we'll be able to figure out what that C is. Oh, that's what fell. Okay. So does it feel like this might be something kind of familiar as we go through here? It's really tied to derivative. This is what we're going to be doing. So we know this about derivatives. So everything we know about derivatives, all we're going to be doing now is going backwards. So there's a couple funky ones. I guess let's go ahead and throw them in here. What if our function, there's only two other types, right? What if our function was the natural log of x? When we go to take its derivative, what do we get? We take the derivative of that. What's the derivative of natural log of x? 1 over x. And remember, it just sort of, it is because it is. There is some mathematics you can kind of sort of prove it, but it actually, when they, in the proof, what they do is they do that and then they take an integral and they show that they match up. So if we wanted to take the integral of 1 over x dx, what would it be? It would be natural log of x plus a constant, right? Because there could be a constant. In this case, it was 0, but we don't know. Okay, so just make that pairing. Since the natural log of x is 1 over x, its integral will be of 1 over x, will take us back to natural log of x. So it's more of a memory thing. There's no real technique to do it. We just have to remember. Then the other one, let me put it up here since we're running out of space, is e to the x. So if our function was e to the x, what is the derivative of e to the x? It's e to the x, right? It's its own derivative, which again is easy but a little bit disconcerting. It doesn't feel like we did anything, right? It doesn't feel quite right. And this is what's also not going to feel quite right. What if we asked to take the integral of e to the x dx? What's that going to equal? E to the x plus a constant, possibly, right? Because it could be 0. Yeah, in this case it's 0, but when we're taking an integral, there's always that possibility there's another constant there. Okay. Again, easy, but doesn't feel quite right because it's its own derivative, it's its own integral. So those are the two that are going to be a little bit tricky. And in the next lesson, on substitution, what we do is, what we're not doing today, we're not taking any derivative that's created because of the chain rule, right? Because the chain rule, really, you took the derivative of the outside and the derivative of the inside. Those are a little bit more complicated. We'll do those next lesson using substitution to make them look a little easier. So there's a technique we'll pick up, but we're just gonna stick with these sort of straightforward derivatives that don't have the product rule, don't have all these fancy stuff, but we will get to places where we'll be able to integrate things that are the result. This is just vocabulary and notation. It's a little bit, I don't try to understand it too clearly, but an antiderivative of a function f is the big F such that the derivative of big F is little f. So I don't know, it kind of confused me, but we start with the derivative. The antiderivative is getting back to the original function. Okay, that's all it is. So whatever notation you want to use, usually in math what happens, the more notation you use, for mathematicians it makes it more exact. For the rest of us people, it makes it more confusing. Okay, and remember, I'm not a mathematician, I'm a math educator. I don't hate math, but it's not a passion of mine either. But I like teaching because when you understand it and you help other people to understand, we can do a lot with it. Okay, so they gave this example, an antiderivative of 4x to the third is x to the fourth. Again, what they did is they added 1 to the exponent and then divided by that new exponent, right? So they got x to the fourth. And notice they're saying it's just one type of antiderivative. They'll talk a little bit later about this plus c. Remember, I just sort of in one slide, we did everything they're going to do step by step. We also call this antiderivative, again, more kind of confusing things. Again, if we start with if we're given an integral, it's always a derivative that we were given. The antiderivative is the answer we're getting back to. We also call it an indefinite integral, and again, that's because of the plus c that they will introduce to us on the next slide. Okay, but we've already seen it because the way we did it. Okay, so the indefinite integral, what is that? It's a set of all antiderivatives. And notice they've got this plus c here of the integral of f of x dx. So just remember, when they're giving us that integral notation, what the function they're giving us is a derivative. And that little dx, that's what it's indicating. When we go through the process of integrating it, we get back to the original function that the derivative was taken from. But as we see, because the process of taking a derivative basically throws the constant away, right? It makes it zero, so it just throws it away. It's gone. It's burnt. Unless there's other evidence, all we can say, well, there was one there, but we don't know what it is. So we put a plus c or a plus k or plus whatever you want, but just some kind of thing that says there's a number here, but we don't know what it is. So this gives us every possible iteration of x to the fourth, right? That this function could come from. If it was x to the fourth plus a million, you take its derivative, you'll get 4x to the third. But the million becomes 0, so the derivative of a million becomes 0. Okay. Does it make kind of sense so far? Okay. The constant of integration, so mathematicians like to give all these sort of formalized names to things. We just call it c. It's a constant of because we integrate it, there's a possible constant here. Well, there's always a constant there, even if it's plus 0 is a constant. We just don't show it. So it just reminds us. And again, if you're a math major, usually the teachers will say, if you forget that plus c on the end, you lose a point or two. I lost lots of points or two because I'd forget to put that. And when you go into the homework and WebAssign, I believe some of them, they will have it embedded. You put your answer, but they've got the plus c for you. Sometimes they don't, so watch for that. If they don't have the plus c, you might be putting in the right answer without the plus c, and they'll say it's wrong. You'll have to put that in. You might be putting it in, but they've already got it. So watch for that. It's just it's a little tricky thing because we go through that. Okay, so just a quick few. Notice the integral of x dx, so they add 1 to the exponent, get x squared. Here's a way, the nice thing about what we're doing now, we can actually check our answers by taking the derivative of our answer. So we got there. If we take the derivative, we should get back to where we started. So let's that's what this is set up. So if we take the derivative of this function, the 2 comes down, subtract 1 from the exponent, 2x to the first divided by 2. Derivative of c is 0, so I'm going to put that as plus 0. The 2's cancel. Plus 0 doesn't, it's just x. That's what we started with. Okay, that worked. Next one, x to the third over 3 plus c. Let's take the derivative. So the 3 comes down. We subtract 1. So we get x squared over 3. 3 divided by 3 is 1. And derivative of any constant is 0. So it's just x squared plus 0, which is just x squared. Hey, good. We check. Okay, so we're able to check our answers once we get what we're doing. And that'll become especially important as we do the other sections, right? Especially the substitution thing. Always take your answer, take its derivative to make sure you go back. If the problem that starts developing here, when you're going back and forth and you're just adding one and subtracting one, it's easy to do the wrong thing at the wrong time, right? Or to subtract one when you're supposed to be adding, to add one when you're supposed to be subtracting, to multiply when you're supposed to be dividing. So watch what you're doing. Again, which direction are we going? We got a function, we take its derivative, we multiply and then subtract one. We've got a derivative, we're going back the other way. I guess I should go this way. We add one to the exponent and then divide by that new exponent. Okay, and here natural log of x plus c. Remember, we already did this. Derivative of natural log is 1 over x. Derivative of c would be 0. So that's 1 over x, which is x, also x to the minus 1 power. So that checks. Okay, so we can always check our answers by, once we integrate, take the derivative. And that's where I see, for me, this is where the derivatives actually made more sense after I got to integration, because you go back and forth. And you're doing it multiple times, things that weren't clear started to become clearer. Okay, and that's why I say just keep on going, and we can still get success even if you haven't gotten it. And so this is just their way of going through each step by step and taking, so I leave these in from the textbook. They did the check. Maybe their writing's nicer than mine, but okay, so calculating indefinite integrals, again, we've already done this, but let's get the formalized rule for it. They say whatever you got, so if you're taking x to some power, x to the n, you just add 1 to the exponent, and you divide by that new exponent, and you have plus a c. So we've done this, like I said, in that first step, we did it. Okay, so this is just the formalized formulas, if you will. Then we get the special one. If we've got x to the minus 1 power, though, that's the one that has a special case. Because usually you can pick this one up, because if you forget, you add 1 to negative 1, what do you get? You get 0. And then you divide by that new one, so you divide by negative 1 plus 1. Oh, wait, I can't divide by 0. Division by 0 is undefined. We can't do it this way. Okay? So that's a good thing, is that at least the one that's sort of the special case, if you try using the general rule, it just won't work. All right? So that would just be x to the 0 over 0. Oops, that doesn't work. It's this special one. And so for me, when I see x to the minus 1, it's actually easier to rewrite it as 1 over x, because that one I'll remember. That's just natural log of x. So that's the one you have to remember. It's different. Okay, that's the one that's different. You're going to integrate x to the minus 1 or 1 over x. We're going to get natural log of x. Okay, one a little different. And they show it in two forms, so either that form or this form. But that's a special case. We'll also see there's the other special case, but that'll come up next. So here's a quick example, just to apply it. Again, we've already done it a couple times. What do we do with x to the 55? First step is to add 1 to the exponent. Good. Second step, divide by that new exponent. I guess the third step, that's what maybe why I always forget it. Even when I teach, I forget about it. The third step plus c, right? Third step plus c. So we just put it all together. 55 plus 1 is 56. 55 plus 1 is 56. plus a constant. And then again, it's always, this is our answer. We could box it in. This is what we're looking for. But it's always good form to do, come back and say, let's check it. So if I took the derivative of x over 50, x to the 56 over 56 plus a constant, what would I do? Taking the derivative, I'll just do it this way. I would bring the exponent down, so that's going to give me 56. 56 divided by 56 cancels. I would subtract 1, so I would have x to the 55, and the derivative of any constant is 0, so that's plus 0, which is at, oh, good, I got back to where I started. Okay, so these first few ones that we're doing today, since they're simple, we won't need to do that, but you want to get in that practice when we go forward, because there's little things that will get left off, like maybe that negative, or maybe you multiplied instead of divided or something, but you'll catch all of that when you go back and take its derivative, and you'll think through it, right? Because you're having to do both backwards and forwards. And again, sometimes that's where I realize that a lot of my difficulties with math is I think bidirectional. I think both ways, and that can be okay. But sometimes when you're supposed to think left to right, I'm thinking right to left, and so we're reading things backwards or the other way around. It's a nice feature to be able to have. I can actually read a book upside down. People will say, "Oh, you want to turn that?" I said, "No, I can read." Sometimes I can read it better upside down because I focus better, but. Yeah, I can read backwards and upside down. Yeah. Leonardo da Vinci used to. He would write backwards so that his text could only be read by most people by putting it in a mirror. It reverses it. But he got so good at it, he actually wrote backwards. But because at that time, if you're a scientist, the church might come and say, "Oh, you're doing illegal stuff," and burn you or whatever they did. So he might, that's his way of doing it. But some of us, we've got various ways that we think, and it's not all set to the dominant ways of doing things. So we think, "Oh, I'm not that smart." No, we're actually very smart in our world, and if we do it in the way our minds work, we just have to figure that out. And that's one of the things I figured out when I did this, is it actually helps me to go both directions. One of my students from Monday was saying, "No, this is more confusing. I'm going to have to go back." So we're all different, okay? We're all different, but we find the ways that work for us personally, and then that's where we get there. Okay, exponential functions. This is one we talked about. Again, it's a very simple one. E to the x is its own integral because it's its own derivative. It goes back and forth, but it at some level, it's still, even after I know it and I say it, I teach it so many times, it still doesn't quite feel right. But it's a very special. It's a very special function. And again, they give the explanation here. There is that one, if we have some other, like an integral 5 to the x dx, when we integrate that, it's going to be its own derivative, but there is a sort of a correcting factor. We looked at that, so we would divide by the natural log of 5, because when you take a derivative of an exponential that's not e to the x, you get this correcting factor, right? So actually e to the x, its derivative is natural log of e to the x, but the natural log of e is 1, right? So we don't worry about it. We just say it's e to the x. We take its derivative. But when we have something that's not e to the x, we need that natural log of the base. Okay, I don't think we do a lot, like on the test they didn't even put, last time they didn't even put that on there, so we'll keep track. But just remember there's that one too. I think we went through some quick examples already, so I did a little bit more. So this is just, again, it's just a formalized way of saying that if you have something that's more than just x to the fifth, or just one term, if you've got multiple terms, you can look at them as multiple functions. So we can take the integral term by term. Okay, so we can just break it off. And that's what we were doing. You could rewrite it that way, but it's not necessary. And it comes from when we take the derivative, we took it term by term, right? We got 5 terms, we take basically 5 derivatives, and we add or subtract them together. That's all it's saying. Okay, but just sort of formally, and we've already done that. The other thing we can do is if we're multiplying by some constant, a constant multiplier, whatever I called it, you can also just say, okay, that constant multiplier is going to stick around, but it doesn't affect anything. And again, we were kind of doing that when we did something like, we had like 4x to the 5th. You could think of that, okay, put the 4 outside, and then take the integral. I guess I should put my dx. So add 1 to the exponent. This is going to be x to the 6. We're going to divide by 6, and then just bring that 4 and multiply, and then you can simplify it, right? Plus a constant. 4 divided by 6, that would be 2x to the 6th over 3. But notice when we simplify a fraction, we lose some of the connection to the original equation up there, that there was actually 4x to the 5th. If we take the derivative, we'll get it back, but sometimes, I kind of like just leaving it like that at least when I can. Okay, so you can see going back and forth. But any constant times is just it's going to stick there. And again, instead of multiplying this time, though, we're going to be dividing by the new exponent. So sometimes gets divided out, sometimes doesn't. Sometimes they're still, that was weird. I think I better go back to bed today. All the mechanical stuffs are doing strange stuff. Motorcycle's been working fine today. No oil. Batteries going out on me. It's not Friday the 13th, though, is it? So I guess I'm safe. Okay. Sum rule. Notice we've got x to the 3rd plus 1, so we could take those individually. Again, we've done this in that first step. So just integrate, and integrating is just the 2 steps backwards, right? First add 1 to the exponent, then divide by that new exponent. Pretty much all we need to do. Constant multiple, again, you could take the 5 and put it outside and just then do it, or you can kind of just leave it. I like to just kind of leave it coming along for the ride, whatever system works best for you. Okay, but we'll show you this because sometimes that's helpful to say, what do I do with this? It's because sometimes these numbers end up being weird, or we got a fraction, and what do I do? Well, let's put it off to the side. Let's integrate the easy part, and then let's bring that back, and then we'll worry about it. And again, you'll see, no, they're just breaking it down. Okay, so now we're going to look at a couple of applications. Let's see, what time is it? Okay, we're good. Okay, so this is where we will have an example of where we're going to be able to figure out what C is. And again, in the homework you'll see you'll be asked to take a few integrals, and you'll have the plus C. You'll be able to take those integrals, have a plus C. There'll be a few ones that will be like this, where they will give you the additional information so you can figure out what C is. So we'll do that here. So the marginal cost to produce a baseball cap. What is a marginal cost? What is a marginal? It's another word for marginal. What's the calculus word for marginal? Derivative. So rate, it's the cost of getting one more. That's what marginals are, which comes directly from the slope of the tangent line, which is the derivative. So yeah, we've got a derivative function. This what they're giving us, dollars per cap, and you'll see that word per, so we know this is a rate, right? So what they're asking us to do, so blah blah blah, production x caps is this, and the cost of producing 100 caps is 500. find the cost function. So find the original cost function, the total cost function, not the marginal. So that means we have to integrate 4 minus 0.001x dx, and then we can get back to the cost function. Okay, what might be throwing you at this point is, why do we need this stuff? We'll see that that is the additional information we need to get what the constant is. Okay, and we'll do that one. So first we just need to integrate. So again, we'll do it term by term. So what is the integral of 4? It's really 4x to the 0, right? So we add 1 to the exponent, and then we divide by that 1. So we get 4 divided by 1, which is 4x to the first power. So 4x, that's the first term of the integrated. Because if we take the derivative of 4x, we get 4, right? So think of that going back and forth. Next, we've got this minus sign, so we'll put the minus. We take the derivative of this, and remember this is x to the first power, so we add 1 to the exponent, and then we divide by that new exponent, which is 2. So x squared, we're going to get an x squared, and then we're going to get 0.001 divided by 2. This is the way I remember how to divide 0.001. Think of it as 0.0010. So think of that last 10. What's 10 divided by 2? It's 5. So this is going to be, again, you could do it with your calculator too. It's going to be 0.0005. Okay, so we go back one. And so we're going to have 0.0005. There's our integral plus a constant. So that is our cost function. But would you run a business that you didn't know what your fixed costs were? I wouldn't. Maybe it's $10,000 to rent the place, or it could be. If I get charged $10,000, I can't make any profit on a house, So we need to know what that constant is, and the way we figure it out is they told us once you have a close function, we know that if you produce, so let's call this h of x for the hat function, or maybe c of x for cat, anyway, that when we take that function and we plug in 100, we need to equal 500. So we take our original function, we take the 4x, and we're going to plug in 100, minus 0.005 times 100 squared, plus a constant, and we know that that has to equal 500. Notice now we've got a function that has only one unknown, which is the constant, and we'll be able to figure it out. Okay, 4 times 100 is 400. 100 squared is 10,000. 1, 2, move it over 3 places. 10,000, so that gives you 1 times 5 should be 5. And again, you could plug that in your calculator just to make sure, but I did this yesterday, so I'm actually doing it more from memory than anything else. Okay, 400 minus 5 is 395, plus a constant, equals 500. So subtract 395 from both sides. And we get that C equals, what's that, 105? And so we can write this function here that our hat function, our cap function, whatever we're going to call it, would be 4x minus 0.0005 x squared plus 105. So now we know what our fixed costs are. Remember, this is a cost function, so fixed cost of $105. We could probably make that up if we make enough hats and sell them for maybe $10 or $15 each. And so now this is looking like a doable business, right? We need those constants of integration. Remember, what we had was the marginal. We don't know how many hats have been produced or anything. We just know the cost of producing one more. That's what the marginal gives us. We know the rate of costs, but we need to know also the total costs when we're doing our business decisions. So having the rate is helpful, but not enough for a complete business evaluation. Knowing the cost is helpful, but knowing how the costs are changing are also, if I'm going to, should I keep doing this business, or are things going to change on me? Those are the kind of things that we can answer with this. Does that make sense? Questions? Okay, so there'll be some questions like that, but again, just remember, every time they give us a function now, you're going to see that something per, dollars per cap, you're going to see it's a rate, it's a derivative. We're going back the other way. Okay. And this is just more verbiage, so I leave this in so it's nicely printed. You can go back and review these, but these are doing all the same thing we did. They're identifying that what they gave us was the derivative, so they need to integrate it, and they do that in 2 steps. And they're using K because they're, now I see, I didn't see that before, but they use C of X for the cap function. I used H of X for the hat function, so that's why they're using K, just so it's not confusing. Okay, you go through, and then they say, yeah, that extra piece of information, you plug in 100, you'll get 500 for your cost, and thus they come up with it step by step. A little bit more words that to read, again, may be helpful. This is our last little section. This will help you with the last problem in the homework. It has something about Galileo. Galilei is throwing some, or Galileo's, what was this? Galileo, anyway. The guy who had the telescope. He threw something and figured out that gravity on Earth has a constant of acceleration. So for this, just remember, and this takes us back to our exam actually, where we started with a position function, right? And what they mean by position function, that will give you the distance traveled, where something's traveling. If we take the derivative, what do we get? Derivative of position became velocity, which is basically, think of it, it's speed, it's directed speed. So this is our velocity. In everyday use, we usually call it just speed. And then if we took the derivative, the second derivative, because that was on the test, which it would be the first derivative of the velocity function, right? What do we get? Acceleration. So what are we going to do now? We're going to start with acceleration, and we're going to integrate to get back to those other two. And that's actually how they determined it, because they could calculate the acceleration of an object in a vacuum, and they saw that that's always constant. So then, as far as gravity is concerned, you can go back and figure out what the speed is going to be, where the position is going to be, all that kind of stuff. And actually, as I was driving in this morning, I think I got a way to explain the units on acceleration now. Okay, so S equals S of t is a position function. And so if we take its derivative, right, here's the derivative of the position function, we get velocity. That's what we just said. I like to give a verbal and then also follow it up with written word, because again, we each learn differently. And then if we took the derivative of the velocity, which is, that's what that is, we get acceleration. So we talked about that. Acceleration is the derivative of velocity. So if we integrate velocity, we get the position. If we integrate acceleration, we get velocity. Okay, so if we can go one way, we can go back the other way. And so if we're given that the velocity of a particle moving in a straight line is given by this function, what would be the position function? Well, we just need to integrate 4t plus 1, right? dt, I guess. So the integral, if we're integrating 4t, what are we going to get? Add 1 to the exponent. We're going to get 4t squared divided by 2. So that, as you start going, you'll just kind of mentally do the addition. 1 plus 1 is 2, divided by 2. And then just remember, when you have a number, when you integrate a number, you're going to get that times x. So it's 1 times x, or t in this case, and then we get a constant. So what is s of t equal? It would be 2t squared plus t plus a constant. And we aren't given any other information, so we can't figure out what that constant is. But now we have a way to figure out, if we know how much time has passed, how much distance, how far that thing has fallen. Before, with the velocity function, we could just, if we knew how much time had passed, we'd know how fast it was going. That might be helpful. But now we could actually also tell, knowing the time, how far it's gone. So again, here they're giving us the same thing. So we're going to see similar stuff. They're just, now they're going to add in sort of an initial condition. The particle is at position s equals 2, so it's gone 2 meters after 1 second. What that's going to allow us to do is to, again, once we integrate, this is what we got to, we can then use that to get what the constant is. So you plug in 1 for t, you know it's got to be equal to 2. Take our function we had, plug in 1 in each place. Actually, I'm going to put that because that was just t. Right, our function was 2t squared plus t plus c. We do that and we see that the constant has to be equal to -1. So now we've got a complete function. We've got the exact function, not just a family of functions, so we can figure out exactly where this particle is at any given time. And again, that was just based on knowing its speed. This is what the police officers will do, like in accident stuff. Sometimes they got skid marks, so they know how long the skid marks is, that they can calculate speed from that, how long it took to stop. If they can track somebody, see what their speed is, they'll know how far they're going. It's all these things are embedded. Sometimes they're embedded into the technology, like a radar gun will tell you all that, can do all those calculations, but it's using this kind of calculus, rates of change. And if we've got a rate of change, we can go back to the other one. So this will be the last step, where we'll start with this constant. So on Earth, a freely falling body accelerates downward at approximately, we're going to go with this one, 32 feet per second in American units. They used to call them British units, but the British don't use them, so I figured why not call them American units, or metric units. And you'll see there's a little slide with this. So we know acceleration is a constant of 32 feet per second. And the way per second, so what that's saying is for each second, the speed picks up by 32 feet per second, okay? Or actually, since we're falling downwards, maybe we would call this negative, right? Because this is, gravity pulls you down. Again, you could think down as positive, whatever, but we'll do it as a negative 32 feet per second. So each second, a little particle that's been dropped, again, assuming there is no air resistance, because feather is not going to drop very fast, but without air resistance, every item on this Earth will pick up speed of 32 feet per second every second. Okay, 32 feet per second is a speed, is a rate, but acceleration means that every second that's getting bigger. Okay, or in this case, more negative. So find an expression for the velocity. So we're going to remember this is the derivative of velocity. So we're going to integrate negative 32. Oops. See what I mean? I even write backwards sometimes. I was going to write 23. 32. It's a constant, so there is no variable there, dt. So we integrate negative 32, and what do we get? We get t to the first power, because this was, again, the way to think of it is t to the 0 power, add 1, divide by 1, we get this, plus a constant, because there's always that integration. And what we're going to see is that constant is, it depends upon what was the initial velocity. So if we just dropped it and didn't add anything, then the constant would be 0. The initial velocity was 0. If we threw it, we gave it some speed to start, it's going to pick up faster. If we threw it up, it's got positive. So that's what we're going to see that constant represents. And so now I'll let them take over, right? They start with this, they integrate, and took them a whole page to get where we did just by talking, right? So basically I said most of this stuff. Okay, so that's our constant, or that's our velocity. Then they tell us, so okay, at time 0, if the velocity is 0, so we're just dropping it, we're not putting any speed on it, we can plug that in and see the constant would be 0. So if you're just dropping something without giving it speed at the beginning, we get this. And then if you do a little bit of work, again, this will just be the last homework problem. It talks about velocity and position and everything. So, velocity is always going to be negative 32t plus whatever the initial speed is. And then if you integrate that, you'll be able to calculate the position. So you might remember from your algebra classes or even the early ones, anytime something was thrown up in the air, you would see this negative 16t squared. That comes directly from that constant of acceleration. This was the initial velocity times t, and then s of t is wherever you started. If you started on top of a mountain that was 500 feet high, that was 500, right? So this is the initial position. You can, since the acceleration due to gravity does not change anywhere on the Earth, you can just sort of remember these or write these down and use them. You don't have to integrate each time. But then you'll be able to do questions like this. And looks like we're about a minute. If you want to see this one, it's on the Monday's video. I did work through this, but again, there's just one problem at the end that does this. You should be just all fine. Thank you all.